Hello there, and welcome to the Scientist Sleepy. Tonight we embark on a gentle exploration, a slow journey to the very edge of time itself, guided by the profound insights of Stephen Hawking. We will delve into the universe's most awe-inspiring secrets, not with a rush, but with the quiet contemplation befitting a deep, restful sleep. Prepare to be captivated by the majestic dance of gravity, the enigmatic nature of black holes, and the very fabric of space-time. Our aim is to unravel these extraordinary phenomena, not as a test, but as a soothing balm for the mind, a lullaby woven from the universe's most fundamental truths. Let us begin our drift. The universe is a symphony of gravity's secrets. Gravity, that invisible architect of the cosmos, orchestrates a grand, silent ballet of stars, planets, and galaxies. It is the fundamental force that shapes the very fabric of space-time, bending and warping it with its immense influence. While we often think of gravity as the force that keeps our feet on the ground, its true nature, as illuminated by the profound insights of physicists like Stephen Hawking, is far more intricate and majestic. Imagine space-time not as a static backdrop, but as a dynamic, elastic sheet. When a massive object like a star is placed upon it, the sheet dips and curves. This curvature is what we perceive as gravity. It dictates the paths of planets in their orbits, the formation of stars, and the majestic spiraling of galaxies. Hawking's work, particularly his contributions to understanding black holes and the early universe, revealed gravity's role in the most extreme environments imaginable. He showed us that gravity isn't just a passive force. It's an active participant in the universe's evolution, a fundamental constant that dictates its destiny. The equations of general relativity, Einstein's masterpiece, describe gravity as the curvature of spacetime caused by mass and energy. This curvature dictates how objects move, not because of a mysterious pull, but because they are following the contours of this warped space-time. Think of a marble rolling on a stretched rubber sheet with a bowling ball in the center. The marble will curve towards the bowling ball, not because the bowling ball is pulling it, but because the sheet is curved. This is the essence of gravity. Hawking delved into the implications of this, exploring how gravity behaves in the most extreme conditions. He considered what happens when matter is compressed to infinite density, creating singularities, points where our current understanding of physics breaks down. He examined the edge of black holes, where gravity is so intense that nothing, not even light, can escape. In these realms, gravity's symphony reaches its crescendo, a testament to its power and mystery. Understanding gravity, even a fraction of it, is to understand the fundamental forces that govern our existence, from the smallest atom to the largest cosmic structures. It is a force that binds us, shapes us, and ultimately connects us to the vast, unfolding story of the universe. The subtle interplay of mass and energy, creating the invisible currents of spacetime, is a profound revelation, suggesting a universe far more interconnected and dynamic than we might initially perceive. This constant, unseen influence is the silent conductor of cosmic harmony, a testament to the elegance and power of nature's most fundamental laws. It's a reminder that even in the stillness of the night, the universe is engaged in a perpetual, graceful dance, guided by the unwavering rhythm of gravity. The secrets it holds are not just about the movement of celestial bodies, but about the very nature of reality itself, a reality woven from the warp and weft of this fundamental force. The symphony of gravity is a lullaby of cosmic order, played out across the vast expanse of existence, a constant, gentle hum that underpins all that is. In the silent hum of existence, gravity's gentle hand shapes the cosmos, reminding us of the profound order woven into the fabric of all things. Black holes are not just cosmic drains, but laboratories of extreme physics. Imagine, if you will, a place in the cosmos so profoundly dense, so utterly inescapable that not even light, the fastest traveler in the universe, can break free from its embrace. These are black holes, and while their name might evoke images of a void, a cosmic drain swallowing everything in sight, Stephen Hawking, along with countless other brilliant minds, revealed them to be far more. They are not mere passive absorbers, but dynamic, enigmatic entities that serve as unparalleled laboratories for testing the very limits of our understanding of physics. At their heart lies the singularity, a point of infinite density where our current laws of physics, both general relativity and quantum mechanics, break down. It's in this extreme environment, near the event horizon, the point of no return, that the most profound and counterintuitive phenomena occur. Here, spacetime itself is so dramatically warped that time, as we perceive it, can stretch and distort in ways that defy everyday experience. An observer falling into a black hole would experience time normally, but to a distant observer, their descent would appear to slow infinitely, their image fading and red-shifting until they vanish, forever trapped beyond the event horizon. But the story doesn't end with inevitable consumption. Hawking's groundbreaking work introduced the concept of Hawking radiation. This theory proposes that black holes are not entirely black, due to quantum effects near the event horizon, where virtual particle-antiparticle pairs are constantly popping into existence and annihilating each other. One particle might fall into the black hole while the other escapes. This escaping particle carries away a tiny amount of energy, meaning the black hole slowly loses mass over an incredibly long period. This process, though infinitesimally slow for stellar mass black holes, suggests that black holes can, in principle, evaporate entirely. This revolutionary idea bridges the seemingly disparate realms of general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of matter and energy at the smallest scales. It's a tantalizing glimpse into a unified theory of physics, one that could finally reconcile these two pillars of modern science. Furthermore, the intense gravitational fields around black holes provide unique conditions to study phenomena like frame dragging, where a rotating black hole can twist the fabric of spacetime around it, carrying objects along for the ride. The study of accretion disks, the swirling disks of gas and dust spiraling into a black hole, allows us to witness matter being heated to incredible temperatures and emitting powerful radiation, offering clues about the extreme conditions that existed in the early universe. Black holes, therefore, are not just cosmic curiosities. They are natural experiments, offering us a front-row seat to the most extreme physics imaginable, pushing the boundaries of our knowledge and inviting us to contemplate the very nature of reality. They are cosmic enigmas that compel us to question, to explore, and to marvel at the profound secrets our universe holds. Within the inescapable embrace of a black hole, the universe whispers its most extreme truths, reminding us that even in the deepest darkness, profound understanding can be found. Spacetime can warp and bend like a fabric under immense weight. Imagine, if you will, a vast, invisible trampoline stretching out in every direction, infinitely. This is our conceptual model for spacetime, the fundamental stage upon which all of reality plays out. It is not a static, empty void, but a dynamic, interwoven tapestry of space and time, a concept revolutionized by the brilliant mind of Albert Einstein through his theory of general relativity. For centuries, we understood gravity as a force, an invisible hand pulling objects towards each other. Newton's law of universal gravitation described this force with remarkable accuracy, explaining why an apple falls from a tree and why the planets orbit the sun. However, it didn't explain how gravity worked, what its underlying mechanism was. Einstein, through his profound insights, proposed a radical departure from this classical view. He suggested that gravity is not a force in the traditional sense, but rather a manifestation of the curvature of spacetime itself. Massive objects like stars and planets are not pulling on other objects with some mysterious force. Instead, they are deforming the very fabric of spacetime around them, creating dips and curves. Think of placing a heavy bowling ball onto that invisible trampoline. The ball creates a significant indentation, a warping of the surface. Now, if you were to roll a smaller marble across the trampoline, it wouldn't travel in a straight line. Instead, its path would be deflected, curving towards the bowling ball as if it were being pulled by an unseen force. This, in essence, is how Einstein explained gravity. The Earth, a massive object, warps the spacetime around it. When the Moon orbits the Earth, it is not being pulled by a force, but rather it is following the curvature in spacetime created by the Earth's mass. Similarly, the Earth orbits the Sun because it is following the deep, curved well in spacetime created by the Sun's immense mass. This warping effect is not limited to the immediate vicinity of massive objects. It extends outwards, influencing the paths of light and the passage of time. Light, though massless, travels through spacetime, and therefore its path is also bent by gravity. This phenomenon, known as gravitational lensing, has been observed and confirmed, where the light from distant galaxies is bent and distorted as it passes by massive objects in the foreground, creating multiple images or arcs of the same distant object. This bending of light is a direct testament to the malleable nature of spacetime. Furthermore, time itself is not absolute, as was once believed. Einstein's theory also dictates that time can be affected by gravity. In regions of stronger gravity, where spacetime is more significantly warped, time actually passes more slowly compared to regions with weaker gravity. This effect, though minuscule in our everyday experience, is measurable and has practical implications. For example, in the functioning of GPS satellites, which must account for the slight difference in time experienced by their clocks due to their position in Earth's gravitational field. The more massive an object, the greater the curvature it induces in spacetime. A star creates a noticeable warp, a planet a lesser one, and a black hole with its incredibly concentrated mass creates an extreme distortion, a region where spacetime is so warped that nothing, not even light, can escape its gravitational pull. This curvature is not a static phenomenon. It is dynamic and responsive to the distribution of mass and energy throughout the universe. The very act of cosmic evolution, the birth and death of stars, the collision of galaxies, all contribute to the ongoing dance of spacetime, shaping the grand cosmic ballet we observe. This understanding of spacetime as a pliable, dynamic entity, capable of bending and warping under the influence of mass and energy, is one of the most profound and elegant achievements of modern physics, offering a completely new perspective on the fundamental nature of gravity and the structure of the universe. The universe is a grand, undulating tapestry, where even the silent dance of stars leaves its gentle imprint on the very fabric of existence. The speed of light is the ultimate cosmic speed limit, unbreakable. Imagine the universe as a vast, silent ocean, and light as the fastest swimmer within it. This swimmer, this constant, unyielding speed, is one of the most profound discoveries of modern physics, largely illuminated by the brilliant mind of Albert Einstein. The speed of light in a vacuum, denoted by the letter c, is approximately 299,792,458 meters per second. That's nearly 300,000 kilometers, or about 186,000 miles, every single second. To put that into perspective, light could circle the Earth about 7.5 times in just 1 second. But this isn't just a very fast speed. It's a fundamental constant, an unbreakable barrier that shapes the very fabric of reality. Einstein's theory of special relativity hinges on this very principle, that the speed of light in a vacuum is the same for all observers, regardless of their own motion or the motion of the light source. This seemingly simple idea has astonishing consequences. As an object with mass approaches the speed of light, its mass increases, and the energy required to accelerate it further becomes infinitely large. Therefore, nothing with mass can ever reach, let alone exceed, the speed of light. This cosmic speed limit isn't a limitation imposed by our current technology. It's an intrinsic property of spacetime itself. It means that the information about events in the universe travels to us at this speed. When we look at distant stars, we are not seeing them as they are now asterisk, but as they were when the light left them, perhaps millions or even billions of years ago. This vast cosmic timescale, dictated by the speed of light, gives us a profound sense of the universe's immense age and scale. It also means that instantaneous communication or travel across interstellar distances, as often depicted in science fiction, is fundamentally impossible within the known laws of physics. The speed of light acts as a cosmic messenger, a constant, reliable signal that allows us to perceive and understand the universe, albeit with a delay that stretches across unimaginable gulfs of time and space. It is the speed at which causality itself propagates. If something were to travel faster than light, it could, in theory, arrive before it left, violating the fundamental principle that cause must precede effect. This unbreakable speed limit, therefore, is not just a physical constraint. It is a cornerstone of our understanding of how the universe works, a silent testament to its ordered and comprehensible nature. It is the universal tempo, the ultimate pace of existence, reminding us that even in the face of infinite possibility, there are fundamental, elegant laws that govern all. The unyielding pace of light whispers of the universe's vastness and the ordered rhythm of time's passage. Time itself can slow down, a relative phenomenon. Imagine the universe not as a static stage upon which events unfold, but as a dynamic, fluid entity, intricately woven with the very fabric of existence. For much of human history, time was perceived as a universal constant, an unwavering clock ticking at the same pace for everyone, everywhere. But Stephen Hawking, building upon the revolutionary insights of Albert Einstein, revealed a far more profound and astonishing truth. Time is not absolute. It is, in fact, relative. This means that time can, and indeed does, slow down. This isn't a philosophical musing. It is a fundamental consequence of the laws of physics, particularly Einstein's theory of special and general relativity. Let's first consider the implications of speed, as described by special relativity. Einstein proposed that the speed of light in a vacuum, approximately 299,792 kilometers per second, is the ultimate speed limit of the universe. Nothing with mass can reach it, and nothing can exceed it. A remarkable consequence of this is time dilation due to velocity. The faster an object moves through space, the slower time passes for that object relative to a stationary observer. If you were to travel at speeds approaching the speed of light, your clock would tick slower than a clock on Earth. For you, a few years might pass, while for those back home, decades or even centuries could have elapsed. This is not science fiction, it's a verified phenomenon. Astronauts on the International Space Station, traveling at speeds around 28,000 kilometers per hour, experience time dilation, albeit to a minuscule degree. Their clocks run ever so slightly slower than ours on Earth. While this difference is imperceptible in our daily lives, it is a tangible demonstration of time's flexibility. The mathematics behind this is elegant. The Lorentz factor derived from Einstein's equations quantifies this slowing of time. As velocity approaches the speed of light, this factor approaches infinity, meaning time would effectively stop for an object reaching that speed. This concept challenges our intuitive understanding of time as a constant, universal flow, suggesting instead that each observer carries their own unique temporal experience, influenced by their motion. But the relativity of time doesn't stop at speed. General relativity introduces another profound factor, gravity. Einstein showed that gravity is not a force in the traditional sense, but rather a curvature of spacetime caused by mass and energy. Massive objects like planets and stars warp the spacetime around them. And just as speed can slow down time, so too can gravity. The stronger the gravitational field, the more spacetime is curved, and the slower time passes. This means that time runs slower for an observer closer to a massive object compared to an observer farther away. For instance, time passes slightly slower for someone on the surface of the Earth than for someone in orbit, because the Earth's gravitational pull is stronger at its surface. This effect, known as gravitational time dilation, is crucial for the precise functioning of technologies like the Global Positioning System, GPS. Satellites in orbit experience both time dilation due to their speed and gravitational time dilation due to being in a weaker gravitational field than on Earth's surface. Without accounting for these relativistic effects, GPS devices would quickly become inaccurate, drifting by kilometers each day. Hawking's work often delved into the extreme implications of these principles, particularly in the context of black holes, where gravity is so immense that time, as we understand it, approaches a standstill. At the event horizon of a black hole, time dilation becomes infinite from the perspective of a distant observer. An object falling into a black hole would appear to slow down and freeze at the event horizon, never quite crossing it, from the viewpoint of someone safely outside. This profound flexibility of time, its ability to stretch and compress based on speed and gravity, reveals a universe far stranger and more wondrous than we might initially imagine. It suggests that our perception of a universal now is an illusion, a localized experience within a grand cosmic tapestry where temporal rhythms vary from place to place and from moment to moment. So time, that relentless current we feel so acutely, is actually a river with varying speeds, its flow dictated by the very structure of the cosmos. Singularities represent the unraveling of our current understanding of physics. Imagine, if you will, the very fabric of our universe, spacetime itself. We understand it as a smooth, continuous tapestry, woven by the presence of mass and energy. General relativity, Einstein's magnificent theory, describes how this fabric bends and warps, creating what we perceive as gravity. It explains the orbits of planets, the bending of starlight, and the grand structure of galaxies. Yet there are points, places within this cosmic tapestry, where our current understanding begins to fray, to unravel, to break down entirely. These are the singularities. What exactly is a singularity? In the context of black holes, it's the theoretical point at the very center where all the mass of the collapsed star is thought to be concentrated. Here, the density becomes infinite and the curvature of spacetime also becomes infinite. Think of it like this. If you were to stretch a rubber sheet and place a tiny marble on it, it would create a gentle dip. Now, imagine trying to place an infinitely dense, infinitely small point on that sheet. The sheet would stretch and tear, becoming infinitely curved. This is the kind of extreme distortion we're talking about at a singularity. The implications of this breakdown are profound. Our laws of physics, as we currently understand them, are built upon the principles of continuity and predictability. They work beautifully in the vast expanses of space and in the everyday realm of our experience. But at the singularity, these laws cease to provide meaningful answers. Density and pressure become infinite, concepts that are physically impossible in our everyday experience. The very equations of general relativity, which so elegantly describe the cosmos, produce nonsensical results, infinities, when applied to these points. This is a signal, a loud and clear one, that our current models are incomplete. Stephen Hawking, in his tireless pursuit of understanding, recognized this fundamental limitation. He argued that the existence of singularities suggests that general relativity, while incredibly successful, is not the final word on gravity. It hints that a more comprehensive theory is needed, one that can reconcile the smooth, continuous nature of spacetime described by relativity with the discrete, probabilistic world of quantum mechanics. Quantum mechanics governs the very small, the realm of atoms and subatomic particles. At these incredibly tiny scales, the universe behaves in ways that are often counterintuitive, governed by probabilities rather than certainties. General relativity, on the other hand, describes the large-scale structure and dynamics of the universe. The challenge of physics today is to find a way to unify these two seemingly incompatible descriptions of reality. Singularities, particularly those at the heart of black holes and at the very beginning of the universe, the Big Bang singularity, are the extreme environments where this unification is most desperately needed. They are the points where the smooth fabric of spacetime predicted by relativity seems to tear, and where the quantum nature of reality might become dominant. It's in these regions of infinite density and curvature that the very concepts of space and time, as we understand them, may cease to exist. Hawking's work, alongside that of Roger Penrose, was instrumental in mathematically demonstrating the inevitability of singularities within the framework of general relativity under certain conditions, like the collapse of a massive star. This wasn't a comfortable discovery. It was a signpost pointing towards the limits of our current knowledge, urging us to look deeper, to seek new theoretical frameworks. It's a reminder that the universe, in its most extreme manifestations, can challenge our most fundamental assumptions about reality. The singularity is not just a theoretical curiosity. It represents a boundary of our comprehension, a stark reminder that the cosmos holds mysteries that lie beyond the reach of our current scientific grasp, pushing us towards a grander, more unified vision of the universe. And so, in the face of these cosmic enigmas, we find a profound stillness, a gentle reminder that our quest for understanding is an ongoing, beautiful journey. Hawking radiation suggests black holes can evaporate over immense timescales. Imagine for a moment the most enigmatic objects in the cosmos, black holes. We often picture them as eternal, inescapable voids, consuming everything that ventures too close, their gravity so profound that not even light can escape. For a long time, this was the prevailing, and indeed, the most intuitive understanding. But Stephen Hawking, with his unparalleled intellect and relentless curiosity, dared to peer even deeper into the heart of these cosmic mysteries, and in doing so, he revealed a breathtaking, counterintuitive truth. He proposed that black holes, far from being eternal prisons, are not entirely black at all. They possess a subtle yet profound emission, a thermal radiation that, over unfathomably long stretches of time, can cause them to shrink and eventually disappear. This revolutionary concept, known as Hawking radiation, emerged from a daring marriage of two seemingly disparate pillars of modern physics: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, the theory that governs the strange and probabilistic world of the very small. Hawking's genius lay in recognizing that at the event horizon of a black hole, the boundary beyond which escape is impossible. The principles of quantum mechanics cannot be ignored, even in the face of overwhelming gravitational forces. To understand this, we must consider the quantum vacuum. In quantum field theory, even seemingly empty space is not truly empty. Instead, it is a roiling, dynamic sea of virtual particles that constantly pop into existence and then annihilate each other in pairs, existing for only the briefest of moments before their existence is erased. Think of it as a constant, fleeting effervescence at the very fabric of reality. Now, when these virtual particle-antiparticle pairs are created very close to the event horizon of a black hole, a peculiar situation can arise. One particle of the pair might fall into the black hole, while its partner, by some quantum fluke, manages to escape. To an outside observer, it appears as though the black hole has emitted a particle. But where did this escaping particle come from? And what happened to its partner? The escaping particle, having seemingly materialized from nowhere, carries away energy. And according to Einstein's famous equation, E equals mc2, energy and mass are interchangeable. So as the black hole emits these particles, it loses a tiny fraction of its mass. This process, though incredibly slow for stellar mass black holes, is continuous. Over billions, trillions, or even vastly greater numbers of years, this steady trickle of Hawking radiation would, in theory, cause a black hole to lose mass, to shrink, and eventually to evaporate entirely. The larger the black hole, the slower this evaporation process. A black hole with the mass of our Sun would take an estimated 1067 years to evaporate, a number so astronomically large it dwarfs the current age of the universe. For supermassive black holes, the behemoths at the centers of galaxies, the timescales are even more immense, stretching to 10,100 years and beyond. This idea of black hole evaporation is deeply profound because it challenges our notion of black holes as ultimate sinks. It suggests that even these cosmic titans are subject to the subtle, pervasive laws of quantum mechanics, and that their seemingly eternal existence is, in fact, finite. It also raises the infamous information paradox. If a black hole evaporates completely, what happens to the information contained within the matter it consumed? Quantum mechanics dictates that information cannot be destroyed. If it is indeed lost, it would represent a fundamental breakdown of our understanding of the universe. Hawking's work on this radiation provided compelling theoretical evidence that information might, in fact, be preserved in some subtle way, perhaps encoded in the outgoing radiation, though the precise mechanism remains a subject of intense theoretical debate and ongoing research. This concept of black holes slowly fading into the cosmic background is a testament to the universe's intricate, interconnected nature, where even the most extreme phenomena are governed by elegant, fundamental principles, and where nothing, not even the seemingly eternal, is truly immutable. The universe whispers secrets of impermanence, even from its most formidable depths. The Big Bang wasn't an explosion asterisk in asterisk space, but the beginning of space. We often visualize the Big Bang as a colossal explosion, a sudden burst of matter and energy erupting outwards into an already existing empty void. This is a common, understandable, but ultimately inaccurate picture. Stephen Hawking, and indeed modern cosmology, paints a far more profound and mind-bending reality. The Big Bang was not an event that occurred asterisk within asterisk space, but rather the very genesis of space and time itself. Imagine, if you can, a state of existence before space, before time, before anything we recognize as here or now. The Big Bang represents the moment when this primordial state transitioned into the universe we inhabit, a universe where space began to expand, carrying with it all the matter and energy that would eventually form stars, galaxies, and ourselves. It wasn't an explosion asterisk into asterisk something, but an unfolding of asterisk everything. Think of it less like a firework in the sky and more like the sky itself being born and stretching outwards. Before the Big Bang, there was no outside for it to explode into. The fabric of space-time, as described by Einstein's theory of general relativity, was itself created and began to stretch. This expansion isn't about galaxies moving through space, but about space itself growing, carrying those galaxies along for the ride. This concept is crucial for understanding the universe's vastness and its ongoing evolution. The initial conditions were incredibly dense and hot, a singularity from which space and time emerged. As space expanded, it cooled, allowing for the formation of fundamental particles, then atoms, and eventually the complex structures we observe today. This ongoing expansion is not a slowing down of an initial blast, but the continued stretching of the cosmic fabric. It means that the universe is not just getting bigger, it is actively creating more space as it grows. This distinction is subtle but fundamental. It shifts our perspective from a universe contained within an infinite expanse to a universe that is the expanse, a self-contained entity that began its journey from an unimaginably compact state. The implications are staggering, suggesting that the very framework of our existence, the stage upon which all cosmic drama unfolds, was itself a product of this singular, foundational event. It forces us to reconsider our intuition about explosions and voids, and to embrace a more abstract, yet ultimately more accurate, understanding of our cosmic origins. The universe did not erupt into pre-existing emptiness. It became the very arena of its own unfolding. This dynamic, self-generating nature of space-time is one of the most awe-inspiring insights into the cosmos, a testament to the universe's capacity for profound mystery and emergent complexity. The Big Bang, therefore, is not a point of origin in space, but the origin of space itself, a cosmic dawn from which all dimensions of existence unfurled. In this grand unfolding, space itself was born, a boundless canvas stretching into an unknown future. The universe is expanding, and that expansion is accelerating. Imagine the universe not as a static canvas, but as a dynamic, ever-stretching tapestry. For much of the 20th century, scientists observed that distant galaxies were moving away from us, a phenomenon first hinted at by Edwin Hubble's groundbreaking work in the late 1920s. He noticed that the light from these galaxies was shifted towards the red end of the spectrum, a phenomenon known as redshift. This redshift, much like the Doppler effect for sound waves where a receding siren's pitch drops, indicated that these galaxies were indeed moving away. The further away a galaxy was, the faster it appeared to be receding. This observation led to the revolutionary conclusion that the universe itself is expanding. Think of it like dots on a balloon being inflated. As the balloon expands, all the dots move further apart from each other, and dots that are already further apart move away at a greater speed. This expansion wasn't an explosion asterisk into asterisk pre-existing space, but rather the expansion asterisk of asterisk space itself, carrying galaxies along with it. It suggested a universe that had a beginning, a concept that eventually led to the Big Bang theory. For decades, this picture of an expanding universe was the prevailing model. Scientists debated whether the expansion would continue forever, or if the gravitational pull of all the matter within the universe would eventually slow it down, perhaps even causing it to contract in a big crunch. The prevailing thought was that gravity, the great cosmic architect and binder, would at least exert a significant braking force on this outward rush. However, in the late 1990s, two independent teams of astronomers, using observations of distant Type Ia supernovae, incredibly bright and consistent stellar explosions that act as standard candles for measuring cosmic distances, made a startling discovery. They found that the expansion of the universe wasn't slowing down as expected. Instead, it was speeding up. This acceleration was utterly unexpected and profoundly puzzling. It implied the existence of some unknown force, a kind of cosmic anti-gravity, pushing everything apart with increasing vigor. This mysterious entity was given the name dark energy. While we can't directly see or feel dark energy, its effects are evident in the accelerating expansion of the cosmos. It's estimated to make up about 70% of the total energy density of the universe, a staggering proportion considering our current understanding of matter and energy. This acceleration has profound implications for the future of the universe. If it continues, galaxies will eventually recede from each other so rapidly that they will disappear beyond our observable horizon, leaving our local group of galaxies isolated in an increasingly empty cosmos. This discovery, that the universe's expansion is not only ongoing but accelerating, has fundamentally reshaped our understanding of cosmology and opened up entirely new avenues of scientific inquiry, pushing us to the very edge of our current knowledge about the fundamental nature of reality. The universe's outward rush, once thought to be slowing, now races ahead, a cosmic tide driven by an unseen hand. Dark energy is the mysterious force driving cosmic acceleration. Imagine the vast, silent expanse of the cosmos, a canvas painted with stars and galaxies, each a distant sun in its own right. For a long time, our understanding of this grand tapestry suggested a universe that, while immense, was perhaps slowing down. The gravitational pull of all the matter within it, the galaxies, the stars, the dust, all seemed to be acting as a cosmic brake, gently decelerating its outward expansion that began with the Big Bang. We pictured a universe that might eventually halt its expansion, perhaps even begin to contract, a slow, graceful descent back into itself. But then, in the late 1990s, a profound discovery emerged, one that shattered these comfortable assumptions and unveiled a startling new reality. Two independent teams of astronomers, meticulously observing distant supernovae, the explosive deaths of massive stars, found something utterly unexpected. These stellar explosions, acting as cosmic lighthouses, were dimmer than they should have been if the universe's expansion was slowing. This dimness indicated they were farther away, meaning the universe hadn't just kept expanding, it had been expanding at an ever-increasing rate. This acceleration, this cosmic push outward, couldn't be explained by the known forces. Gravity, the dominant force on large scales, is attractive. It pulls things together. What then could be pushing everything apart with such relentless vigor? Scientists began to theorize about a new, invisible component of the universe, something that permeated all of space and exerted a negative pressure, acting as an anti-gravitational force. This enigmatic entity was given a name: dark energy. Unlike dark matter, which we infer from its gravitational effects on visible matter, dark energy is a more abstract concept, a placeholder for the observed phenomenon of accelerated expansion. Its exact nature remains one of the most profound mysteries in modern cosmology. Is it an intrinsic property of spacetime itself, a kind of cosmic vacuum energy that, as space expands, creates more of itself, driving further expansion? This idea aligns with Einstein's cosmological constant, a term he once introduced and later called his biggest blunder, but which now seems to be making a comeback. Or is dark energy something else entirely, a dynamic field that changes over time, a relic from the early universe that is only now becoming dominant? The implications of dark energy are staggering. It suggests that the vast majority of the universe, Some estimates place it at around 68% of the total energy density, is composed of this invisible, accelerating force. This means that the familiar matter and energy we can observe, the stars, planets, and ourselves, are but a small fraction of the cosmic whole. As the universe continues to expand at an accelerating rate, galaxies will eventually recede from each other so rapidly that they will disappear beyond our observable horizon, leaving our local group of galaxies isolated in an ever-emptying void. The very fabric of spacetime is being stretched, not by a gentle breeze, but by a powerful, unseen current. It's a humbling realization, a reminder of how much we still have to learn about the fundamental nature of reality. The universe, it seems, is not just expanding, it's actively pushing itself apart, driven by an energy we can only perceive through its grand, cosmic consequences. This invisible hand is shaping the destiny of the cosmos, guiding its ultimate fate in ways we are only just beginning to comprehend, revealing a universe far stranger and more dynamic than we ever imagined. Dark energy, the unseen architect, whispers of an ever-widening future, a cosmic breath that expands all horizons into the quiet unknown. Dark matter is the invisible scaffold holding galaxies together. Imagine the night sky, a breathtaking tapestry of stars, nebulae, and galaxies. We see the luminous matter, the stars, the gas, the dust, that emits light and thus reveals itself to our telescopes. But what if I told you that this visible matter, as magnificent as it is, represents only a fraction, perhaps as little as 15% of the total matter in the universe? The vast majority, a staggering 85%, is composed of something entirely unseen, something we call dark matter. It's a profound mystery, a cosmic enigma that has reshaped our understanding of the universe's structure and evolution. For decades, astronomers observed peculiar behaviors in galaxies that couldn't be explained by the visible matter alone. Stars on the outer edges of galaxies were observed to be orbiting their galactic centers at speeds far too high to be held in place by the gravitational pull of the visible stars and gas. According to the laws of gravity as we understand them, these stars should have been flung out into intergalactic space, leaving the galaxies to disintegrate. Yet they remain, bound in their celestial dance. This discrepancy led to the hypothesis of dark matter, an invisible substance that exerts a gravitational influence, providing the extra oomph needed to keep galaxies intact. It's as if the visible parts of a galaxy are merely decorations on a much larger, invisible structure. This dark matter isn't like ordinary matter. It doesn't interact with light in any significant way. It doesn't absorb, reflect, or emit light, making it utterly invisible to our optical instruments. It also seems to interact very weakly, if at all, with ordinary matter except through gravity. This means it doesn't clump together to form stars or planets, nor does it form clouds of gas that we can detect. Its presence is inferred solely by its gravitational effects on the visible universe. Think of it like the wind. You can't see the wind itself, but you can see its effects. The rustling leaves, the bending trees, the sails of a ship filled. Similarly, we can't see dark matter, but we observe its gravitational influence on stars, galaxies, and even the large-scale structure of the cosmos. This unseen scaffolding is crucial for the formation of galaxies themselves. In the early universe, tiny fluctuations in density were amplified by gravity. Regions with slightly more matter, including dark matter, attracted more matter, eventually collapsing to form the vast cosmic structures we see today. Dark matter, being more abundant and not subject to the same forces that prevented ordinary matter from collapsing as easily in the early universe, played a pivotal role in seeding these structures. Without dark matter, the universe would likely be a much more uniform and less interesting place, devoid of the intricate galactic formations that inspire such wonder. Scientists are actively trying to detect dark matter particles directly through various experiments, often located deep underground to shield them from other cosmic radiation. These experiments look for rare interactions between hypothetical dark matter particles and the detectors. While the exact nature of dark matter remains one of the most significant unanswered questions in physics and cosmology, its existence is overwhelmingly supported by a wealth of observational evidence, from the rotation curves of galaxies to the gravitational lensing of light around massive objects, and the patterns seen in the cosmic microwave background radiation. It is the silent architect, the unseen foundation upon which the visible universe is built, a testament to the profound mysteries that still lie beyond our immediate perception. In the silent expanse, an invisible hand guides the cosmic ballet, holding stellar dreams together. The cosmic microwave background is the echo of the early universe. Imagine, if you will, peering back through the unfathomable expanse of time, not with a telescope that gathers light from distant stars, but with a unique instrument that listens to the very whispers of creation itself. This is the profound gift of the cosmic microwave background, or CMB. It is not merely radiation. It is a snapshot, a fossilized imprint of the universe in its infancy, a time when it was a mere 380,000 years old. Prior to this epoch, the universe was a roiling, opaque plasma, a dense soup of charged particles, electrons and protons, and energetic photons, all interacting so intensely that light could not travel freely. It was like being trapped within a thick, luminous fog. But as the universe continued its relentless expansion, it also cooled. Eventually, a critical threshold was reached. The temperature dropped enough for electrons and protons to combine, forming neutral atoms. This pivotal moment, known as recombination, dramatically changed the universe's character. Suddenly, the photons, which had been constantly scattering off free electrons, were free to travel unimpeded. They streamed outwards in all directions, carrying with them the imprint of the conditions that existed at that very instant. These photons, initially carrying a spectrum of energies corresponding to that early, hot universe, have been traveling ever since. And as the universe has continued to expand over the subsequent 13.8 billion years, these ancient photons have been stretched, their wavelengths elongated, their energies diminished. This stretching has shifted their frequency from visible light and infrared into the microwave portion of the electromagnetic spectrum. This is the cosmic microwave background radiation we detect today. It bathes the entire sky, a faint, nearly uniform glow, a testament to the universe's homogeneous beginnings. However, the CMB is not perfectly uniform. Within this seemingly smooth background, there are incredibly subtle temperature fluctuations, tiny variations on the order of parts per 100,000. These minuscule differences are of paramount importance. They represent the seeds of all the structure we see in the universe today: the galaxies, the clusters of galaxies, the vast cosmic web. These slight overdensities and underdensities in the early plasma, amplified by gravity over billions of years, are the cosmic blueprints from which everything has grown. The study of these anisotropies, these subtle patterns in the CMB, has revolutionized our understanding of cosmology. Missions like COBE, WMAP, and the Planck satellite have mapped these variations with exquisite precision, allowing scientists to determine fundamental parameters of our universe, such as its age, its composition, the proportions of dark matter, dark energy, and ordinary matter, and the geometry of spacetime. It is as if we have been given a cosmic Rosetta Stone, a way to decipher the very language of the early universe. The CMB is a constant, gentle reminder that our present reality is built upon an ancient, luminous past, a past that continues to inform and shape the cosmos we inhabit. It is a tangible link to the universe's fiery birth, a persistent echo that resonates through the vastness of space and time, carrying with it the story of our cosmic origins, a story written in the faint glow of ancient light. The universe's first light, stretched by eons, whispers the secrets of its own beginning, a calm assurance of cosmic continuity. Quantum mechanics governs the tiny, unpredictable realm of particles. At the very heart of reality, far beneath the familiar scale of our everyday world, lies a realm of profound strangeness and exquisite beauty, the domain of quantum mechanics. This is where the fundamental building blocks of the universe, the electrons, photons, quarks, and countless other subatomic entities, perform their ceaseless, intricate dance. Unlike the predictable, clockwork-like mechanics that govern planets in orbit or billiard balls colliding, the quantum world operates on principles that often defy our common-sense intuition, a testament to the universe's capacity for the extraordinary. Here, particles don't behave like tiny, solid marbles, but rather as ephemeral waves of probability, existing in multiple states simultaneously until observed. This concept, known as superposition, is one of the cornerstones of quantum theory. Imagine a coin spinning in the air, neither heads nor tails until it lands. A quantum particle, in a sense, can be both heads and tails at the same time, existing in a blurry state of potential until an interaction forces it to choose a definite outcome. This inherent uncertainty, this probabilistic nature, is not a limitation of our measurement tools, but a fundamental characteristic of reality at its smallest scales. Another mind-bending principle is entanglement, where two or more particles become so deeply linked that they share the same fate, regardless of the distance separating them. If you measure a property of one entangled particle, you instantaneously know the corresponding property of the other, a phenomenon Einstein famously called spooky action at a distance. This interconnectedness suggests a hidden, underlying unity to the universe, a cosmic web woven from the quantum threads of existence. The energy of these particles is also quantized, meaning it exists in discrete packets, or quanta, rather than flowing continuously. This is why light, for instance, is composed of photons, individual packets of electromagnetic energy. These quanta are the fundamental units of energy, charge, and momentum, the very currency of the subatomic world. The rules of quantum mechanics dictate how these particles interact, how they form atoms, and how those atoms, in turn, build everything we see and touch. It is the bedrock upon which chemistry, biology, and indeed all of material science are built. Despite its strangeness, quantum mechanics has been tested and verified with extraordinary precision, forming the basis for many of our modern technologies, from lasers and transistors to magnetic resonance imaging, MRI, and the nascent field of quantum computing. Stephen Hawking, though primarily known for his work on gravity and cosmology, deeply appreciated the profound implications of quantum mechanics, particularly when considering the extreme conditions found within black holes and at the very beginning of the universe. He recognized that a complete understanding of these phenomena would require a synthesis of general relativity and quantum mechanics, a unified theory that remains one of the greatest challenges in modern physics. The quantum realm, with its inherent uncertainty and interconnectedness, reminds us that reality is far more nuanced and mysterious than our macroscopic experiences might suggest. It is a universe of potential, of probabilities, and of surprising deep connections. In the quantum whispers of existence, we find not chaos, but a deeper, more intricate order, where uncertainty itself paints the canvas of creation. general relativity, describes the grand dance of gravity and space-time. Imagine the universe not as a static stage upon which events unfold, but as a dynamic, interconnected entity, a fluid tapestry woven from the very fabric of existence. This is the profound insight at the heart of Albert Einstein's general theory of relativity, a cornerstone of our modern understanding of the cosmos, and a concept Stephen Hawking deeply explored. For centuries, we understood gravity as a mysterious force, an invisible tether pulling objects towards one another, as described by Isaac Newton. But Einstein, with his revolutionary thinking, reimagined gravity entirely. He proposed that gravity is not a force in the traditional sense, but rather a manifestation of the curvature of spacetime. Spacetime, a unified four-dimensional continuum of three spatial dimensions and one dimension of time, is not a passive backdrop. Instead, it is a pliable, elastic medium that can be warped, stretched, and bent. Massive objects like stars and planets create indentations in the spacetime fabric, much like placing a heavy ball on a stretched rubber sheet. This indentation is what we perceive as gravity. When another object, say a smaller planet or a meteor, travels near this massive object, it doesn't follow a straight line. It follows the curves in spacetime created by the larger mass. This curved path is what we interpret as the object being pulled by gravity. The more massive an object, the greater the curvature it creates, and thus, the stronger its gravitational influence. This elegant idea explained anomalies in planetary orbits that Newtonian physics couldn't, and it led to astonishing predictions, such as the bending of light by gravity. Light, though massless, travels through spacetime, and therefore, its path is also deflected by the curvature caused by massive objects. This bending of starlight by the sun was famously confirmed during a solar eclipse, providing crucial evidence for general relativity. Furthermore, general relativity revealed that time itself is not absolute. The passage of time is influenced by gravity. It flows more slowly in stronger gravitational fields. This means that time near a massive object ticks at a slightly different rate than time far away from it. This effect, known as gravitational time dilation, is not just a theoretical curiosity. It has practical implications, for example, in the precise timing required for GPS satellites to function accurately. The elegance of general relativity lies in its ability to unify gravity with the geometry of spacetime, offering a coherent and predictive framework for understanding the large-scale structure and dynamics of the universe. It paints a picture of a cosmos where mass and energy dictate the shape of spacetime, and the shape of spacetime, in turn, dictates the motion of mass and energy. It is a cosmic ballet, a grand dance choreographed by the interplay of matter and geometry, a fundamental principle that underlies the very existence and evolution of the universe as we perceive it. Hawking, throughout his work, delved into the implications of this theory, particularly at the extreme conditions found near black holes, where spacetime is warped to an unimaginable degree, and the very concepts of space and time begin to break down. He used general relativity as the foundation to explore the most enigmatic objects in the universe, pushing the boundaries of our comprehension of gravity's ultimate dominion. In the grand theater of the cosmos, gravity is the unseen choreographer, shaping the very stage upon which all existence plays out. The quest for a unified theory aims to marry these two pillars. For much of the 20th century, two monumental pillars of physics stood, describing the universe with breathtaking accuracy, yet in fundamentally different ways. On one hand, we have Einstein's general relativity, a masterpiece of geometric intuition, describing gravity not as a force, but as the curvature of spacetime itself, a grand, elegant tapestry woven by mass and energy. It governs the colossal, the orbits of planets, the bending of starlight around stars, the majestic dance of galaxies, and the very evolution of the cosmos. General relativity paints a picture of a smooth, continuous universe, where the fabric of reality can be stretched and warped. It's a theory of the large, the macroscopic, the predictable in its grand sweep. On the other hand, we have quantum mechanics, a realm of the infinitesimally small, a world of probabilities and inherent uncertainty. It describes the fundamental forces of nature, electromagnetism, the strong nuclear force and the weak nuclear force, not through smooth curves, but through the exchange of discrete packets of energy, called quanta, mediated by fundamental particles. Think of it as a universe built from tiny, jittery building blocks, where particles can exist in multiple states at once, and where observation itself can influence reality. Quantum mechanics is the theory of the subatomic, the bizarre, the profoundly counterintuitive. The trouble arises when we try to apply both theories simultaneously, particularly in extreme conditions. Imagine the heart of a black hole, a singularity where gravity is infinite and the universe is compressed to an unimaginably small point. Here, general relativity breaks down, predicting infinities that physicists find deeply unsatisfying. Similarly, when we consider the very early moments of the universe, the Big Bang itself, a period of immense energy concentrated in a tiny volume, both theories seem to clash. Quantum mechanics, with its inherent fuzziness, struggles to coexist with the smooth, deterministic spacetime of general relativity. It's like trying to use a blueprint for a skyscraper to design a single atom. The scales and principles are just too different. This is where the quest for a unified theory, or a theory of everything, comes in. It's the grand ambition of theoretical physics to find a single, overarching framework that can encompass both general relativity and quantum mechanics, explaining all fundamental forces and particles within a single, consistent mathematical structure. It's about finding the underlying, fundamental language of the universe, a language that speaks to both the cosmic ballet of planets and the frantic dance of subatomic particles. Stephen Hawking, a titan in this pursuit, was deeply invested in understanding these extreme environments where our current theories falter. His work on black holes, particularly the concept of Hawking radiation, was a significant step in bridging the gap between quantum mechanics and gravity. By applying quantum field theory in the curved spacetime around a black hole, he demonstrated that black holes are not entirely black, but emit a faint radiation, a process that hints at a deeper connection between these two seemingly disparate realms. It suggests that gravity itself might have quantum properties, and that the smooth fabric of spacetime might, at its most fundamental level, be a quantum phenomenon. This quest is not merely an academic exercise, it's a profound exploration of reality itself. It seeks to answer some of the deepest questions about our universe. What happened at the very instant of the Big Bang? What is the true nature of a black hole's singularity? Is our universe the only one, or are there others? A unified theory would provide a more complete and coherent picture of existence, one that reconciles the seemingly contradictory descriptions of the cosmos that we currently possess. It's the ultimate scientific dream, to find the single, elegant truth that underlies all physical phenomena, from the smallest subatomic particle to the largest cosmic structure. The challenge is immense, requiring entirely new ways of thinking about space, time, gravity, and matter. Theories like string theory and loop quantum gravity are current contenders, each proposing different fundamental constituents of reality and different ways to reconcile the quantum and the gravitational. These theories suggest that at the most fundamental level, Reality might not be made of point-like particles and smooth space-time, but of tiny vibrating strings or quantized loops of space itself. This endeavor is a testament to humanity's insatiable curiosity, our drive to understand the universe not just in its observable parts, but in its deepest, most fundamental workings. It's a journey towards a more complete, more profound understanding of the reality we inhabit, a reality that, at its core, may be far more unified and interconnected than we can currently perceive. And so, the universe whispers its secrets, inviting us to listen, to ponder, and to find harmony in its grand, unified song. The information paradox. What happens to information falling into a black hole? Imagine, if you will, a cosmic mystery that stretches the very limits of our understanding, a puzzle that Stephen Hawking himself grappled with for decades. The information paradox. It's a question that probes the fundamental nature of reality, asking what becomes of the detailed characteristics of matter and energy when it encounters the ultimate cosmic abyss, a black hole. In our everyday experience, information is never truly lost. If you burn a book, the ashes, smoke, and heat still contain, in principle, all the information that was once within the pages. This principle, known as the conservation of information, is a cornerstone of quantum mechanics, the theory that governs the universe at its smallest scales. However, black holes, as described by Einstein's theory of general relativity, seem to present a radical exception. When matter falls into a black hole, it crosses an event horizon, a point of no return. According to classical general relativity, anything that crosses this boundary is irretrievably lost, its unique properties ceasing to exist in our observable universe. But then, Hawking's groundbreaking work on Hawking radiation introduced a new layer of complexity. He proposed that black holes are not entirely black. They slowly emit thermal radiation, a process that causes them to lose mass and eventually evaporate over unfathomable timescales. If a black hole evaporates completely, and the information that fell into it is truly gone, then the conservation of information is violated. This is the heart of the paradox, a conflict between two of our most successful physical theories. How can the universe, at its deepest levels, seemingly break its own rules? Scientists have proposed various ingenious solutions. One idea is that the information is somehow encoded in the Hawking radiation itself, perhaps in subtle correlations that are incredibly difficult to detect. Another possibility is that the information is preserved in a remnant, a tiny, stable object left behind after the black hole has evaporated. Some theories even suggest that the information might be transferred to another universe, or that our understanding of spacetime itself needs a radical revision, perhaps involving concepts like wormholes or holographic principles, where the information of a volume of space is encoded on its boundary. The information paradox isn't just an abstract theoretical conundrum. It's a profound question about the consistency and completeness of our physical laws. It forces us to confront the possibility that our current models, while incredibly powerful, may be incomplete, and that a deeper, more unified theory of quantum gravity is needed to reconcile the seemingly irreconcilable. The journey to resolve this paradox is a testament to the human drive to understand the universe, even when faced with its most bewildering enigmas. It's a reminder that the cosmos holds secrets far grander and more mysterious than we can easily imagine, and that the pursuit of knowledge often leads us to the very edge of what we thought was possible. The enigma of a black hole's embrace is a whisper of cosmic laws we are still striving to comprehend. The multiverse hypothesis proposes countless other universes. Imagine for a moment that our universe, vast and awe-inspiring as it is, might not be the only one. This is the essence of the multiverse hypothesis, a profoundly mind-bending idea that suggests our observable cosmos is but one bubble in an infinite cosmic ocean, or perhaps one page in an unimaginably large library of realities. This isn't merely a fanciful notion from science fiction. It arises from several serious avenues of scientific inquiry, particularly in cosmology and quantum physics. One prominent source of multiverse ideas comes from the theory of cosmic inflation, the rapid expansion of the universe in its earliest moments. If inflation occurred, it might not have stopped everywhere simultaneously. Instead, some regions of spacetime could have continued inflating, spawning new bubble universes that pinch off from our own, each with potentially different physical laws and fundamental constants. Think of it like boiling water. Bubbles form and separate. In this scenario, our universe is just one such bubble that stopped inflating, allowing matter and structure to form within it. Another perspective arises from quantum mechanics. The many worlds interpretation of quantum mechanics proposed by Hugh Everett III suggests that every time a quantum measurement is made, the universe splits into multiple branches, with each possible outcome of the measurement occurring in a separate universe. So, if a quantum event has a 50% chance of happening one way and a 50% chance of happening another, the universe divides, and in one universe, it happens one way, and in another, it happens the other. This leads to an ever-branching tree of realities, each representing a different history, a different set of choices, and ultimately, a different universe. Furthermore, some theories, like string theory, which attempts to unify all fundamental forces and particles, require extra spatial dimensions beyond our familiar three. The way these extra dimensions are compactified or curled up could vary, leading to different sets of physical laws in different regions of a larger, overarching landscape of possibilities, each constituting a distinct universe. These hypothetical universes might be vastly different from our own. Some could be barren and lifeless, while others might harbor entirely different forms of existence, governed by physics we can barely comprehend. The very constants that seem so precisely tuned for life in our universe, the strength of gravity, the charge of an electron, the mass of a proton, might be different elsewhere. This offers a potential, albeit speculative, solution to the fine-tuning problem, the observation that our universe's constants appear remarkably well-suited for the existence of life. If there are countless universes with varying constants, it's not surprising that we find ourselves in one where those constants allow for our existence. We simply wouldn't be here to observe it otherwise. The multiverse concept pushes the boundaries of our understanding, challenging our perception of reality and our place within it. While direct observational evidence for other universes remains elusive, the theoretical underpinnings are compelling, prompting scientists to explore these far-reaching implications. It's a testament to the boundless curiosity of the human mind, reaching out to grasp the ultimate nature of existence, even if it means contemplating realities beyond our immediate reach. In the grand tapestry of existence, our universe may be but a single, exquisite thread, part of a boundless, unseen weave of infinite possibility. Cosmic inflation explains the flatness and uniformity of our universe. Imagine, if you will, the very earliest moments of our universe, a fraction of a second after the Big Bang. It was an era of unimaginable energy and density, a primordial soup from which everything we see, and indeed everything we asterisk our asterisk, would eventually emerge. For decades, cosmologists grappled with a perplexing observation about this nascent cosmos. It appeared remarkably flat and astonishingly uniform. Let's break down what those terms mean. When we speak of the universe being flat, we're referring to its geometry. In physics, Flatness implies that if you were to send out parallel rays of light, they would remain parallel forever, never converging or diverging. Think of a perfectly flat sheet of paper extending infinitely in all directions. This geometric property is directly related to the total energy density of the universe, the sum of all matter, energy, and even the mysterious dark energy. If this density were slightly higher, the universe would curve in on itself, eventually collapsing. If it were slightly lower, it would expand forever, with light rays diverging. The observed flatness, to an astonishing degree of precision, suggests that the universe's density is incredibly close to a critical value. This precision is, in itself, a profound puzzle. Why should the initial conditions be so perfectly balanced to achieve this flatness? It's akin to balancing a pencil on its tip for billions of years. Then there's the uniformity, or isotropy, and homogeneity. If you look out at the universe on the largest scales, it appears remarkably the same in every direction and in every location. The cosmic microwave background radiation, the faint afterglow of the Big Bang, is almost perfectly uniform in temperature across the entire sky. This means that regions of the early universe that were, by conventional understanding, causally disconnected, meaning light wouldn't have had time to travel between them, somehow managed to reach the same temperature. How could two vastly separated patches of the early universe know about each other's temperature to match it? This is known as the horizon problem. Without a mechanism to reconcile these vast, seemingly disconnected regions, the observed uniformity remains a profound mystery. Enter the concept of cosmic inflation, a brilliant theoretical idea proposed by Alan Guth and further developed by others like Andre Linde and Paul Steinhardt. Inflation suggests that in an infinitesimally brief period, perhaps from 10.3 to 10.32 seconds after the Big Bang, the universe underwent an exponential expansion, growing in size by a factor of at least 1026, and possibly much, much more. Imagine a tiny, perhaps even quantum-sized, region of space suddenly stretching at an astonishing rate, like a balloon being blown up at a speed far exceeding the speed of light. While nothing within asterisk spacetime can travel faster than light, spacetime itself can expand at any rate. This rapid, explosive growth during inflation elegantly solves both the flatness and uniformity problems. Firstly, consider the flatness. Any initial curvature, any deviation from perfect flatness, would have been stretched out and smoothed over during this period of immense expansion. Think of taking a crumpled piece of paper and stretching it to an enormous size. Any initial wrinkles would become virtually imperceptible. Inflation effectively flattens out the geometry of the universe, making it appear flat on the scales we observe today, regardless of its initial, potentially curved, state. Secondly, inflation addresses the horizon problem. Before inflation began, the entire observable universe today was contained within a tiny, causally connected region. This means that all parts of this primordial patch could interact and exchange thermal energy, allowing them to reach a uniform temperature. Then, inflation took this tiny, uniform region and stretched it to an immense size, far beyond what we can currently observe. The regions that appear causally disconnected to us today were, in fact, in close contact before inflation inflated them to their current vast separation. The uniformity we observe is a relic of that initial, tiny, uniform patch. Inflation essentially blows up a small, uniform and flat region to become the vast, uniform and flat universe we inhabit. This period of accelerated expansion, driven by a hypothetical, inflattened field, not only smoothed out the universe, but also provided the seeds for the large-scale structures we see today. Tiny quantum fluctuations, present even in the earliest moments, were amplified by inflation to macroscopic scales, becoming the primordial density variations that would eventually coalesce under gravity to form galaxies, stars, and planets. These tiny ripples in the fabric of spacetime, stretched to cosmic proportions, are the fundamental reason why the universe is not perfectly uniform, but has the intricate cosmic web of structures we observe. Inflation, therefore, is a cornerstone of modern cosmology, providing a compelling explanation for the fundamental characteristics of our universe's large-scale structure and geometry. The vastness of the cosmos is a canvas painted by the echoes of its earliest, most rapid breath. The cosmological constant might be the key to understanding dark energy. Imagine, if you will, the vast, silent expanse of the cosmos. For decades, astronomers observed that the universe wasn't just expanding, but that this expansion was, in fact, accelerating. This was a profound, almost unsettling discovery. It implied the existence of some unknown force, a cosmic push that was overcoming the gravitational pull of all matter. This mysterious influence, this cosmic acceleration, was eventually termed dark energy. Now the question naturally arose: what is this dark energy? Where does it come from? For a long time, it remained one of the most perplexing enigmas in modern cosmology. But in the grand tapestry of scientific inquiry, threads often connect in unexpected ways, revealing patterns that were previously hidden. And here, the story of dark energy begins to intertwine with a concept that has a surprisingly long and complex history: the cosmological constant. The cosmological constant, often denoted by the Greek letter lambda, was first introduced by Albert Einstein in his theory of general relativity. He initially conceived of it as a way to counteract gravity, to create a static universe. At the time, the prevailing scientific view was that the universe was unchanging, eternal, and neither expanding nor contracting. Einstein's equations, however, naturally suggested a dynamic universe. To force his equations to allow for a static universe, he added this constant term, a sort of universal repulsion that would balance the inward pull of gravity. It was, in a sense, a cosmic balancing act. However, when Edwin Hubble's observations in the late 1920s provided compelling evidence that the universe was indeed expanding, Einstein famously, and some say regretfully, abandoned the cosmological constant. He referred to its introduction as his biggest blunder. For many years, it was largely forgotten, a curious footnote in the history of physics. But as the evidence for accelerating expansion mounted in the late 20th century, cosmologists began to revisit the idea. What if, instead of being a blunder, Einstein's constant was actually a prescient glimpse into the fundamental nature of the universe? What if the vacuum of space itself, that seemingly empty void, possessed an inherent energy density that was driving this acceleration? This concept aligns remarkably well with the observed properties of dark energy. The cosmological constant in this modern interpretation represents the energy density of the vacuum. It's a property of spacetime itself, a fundamental aspect of the universe's fabric. Unlike matter or radiation, which dilute as the universe expands, the energy density of the vacuum, if it is indeed the cosmological constant, remains constant. This means that as the universe grows larger, the total amount of dark energy increases, leading to a stronger repulsive force and an ever-accelerating expansion. It's a subtle yet profound shift in perspective. Instead of a new, exotic substance permeating the cosmos, dark energy could be an intrinsic feature of the universe's very existence. It suggests that emptiness is not truly empty, but pregnant with a subtle, pervasive energy. The implications of this are staggering. If the cosmological constant is indeed the correct explanation for dark energy, it means that the universe is not only expanding, but this expansion will likely continue indefinitely, perhaps forever. This has profound consequences for the ultimate fate of the cosmos, suggesting a future of increasing emptiness and isolation, a scenario sometimes referred to as the Big Freeze or heat death. The precise value of this cosmological constant is also a subject of intense study. Theoretical calculations based on quantum field theory predict a vacuum energy density that is orders of magnitude larger than what is observed. This discrepancy, known as the cosmological constant problem, remains one of the most significant unsolved puzzles in physics, hinting that our current understanding of quantum gravity or the nature of the vacuum is incomplete. However, the fact that the observed value of dark energy is small, positive, and constant aligns so beautifully with the concept of a cosmological constant makes it the leading candidate for explaining the universe's accelerating expansion. It's a testament to the power of revisiting old ideas with new perspectives, and a reminder that sometimes the most profound secrets are hidden in plain sight, within the very structure of reality. The silent hum of an ever-expanding void whispers a constant, subtle push, a reminder that even emptiness holds a profound, accelerating energy. The fine-tuning problem. Why are the universe's constants so perfect? Imagine, if you will, a cosmic instrument meticulously crafted, not by hands but by the very laws that govern existence. Stephen Hawking and many before and after him pondered a profound puzzle, the apparent fine-tuning of the universe's fundamental constants. These aren't just numbers, they are the bedrock upon which reality is built. If these constants were even minutely different, our universe as we know it simply could not exist. Consider the cosmological constant, a measure of the energy density of empty space. If it were just slightly larger, the universe would have expanded so rapidly after the Big Bang that matter would never have had the chance to clump together to form stars and galaxies. If it were even slightly smaller, gravity might have caused the universe to collapse back on itself almost immediately. Then there's the strength of the electromagnetic force, which dictates how atoms bond. If it were a tiny bit stronger, protons would repel each other so fiercely that no atomic nuclei beyond hydrogen could form. If it were a bit weaker, stars would burn out too quickly, or perhaps wouldn't ignite at all, failing to create the heavier elements necessary for life. The gravitational constant, the force that pulls objects together, is another critical player. A slightly different gravitational constant would mean stars would either be too hot and burn out too fast, or too cool to fuse elements. Even the mass difference between protons and neutrons is remarkably precise. If this difference were altered, all neutrons would have decayed, or all protons would have fused with electrons, preventing the formation of stable atoms. These aren't isolated quirks, they are a symphony of exquisite balance. The sheer improbability of these values arising by chance, given the vast range of possibilities, leads to the fine-tuning problem. It suggests either a deliberate design, a statistical anomaly of unimaginable scale, or perhaps a hint that our understanding of the universe is incomplete, that there might be mechanisms at play we haven't yet grasped. This puzzle is not merely an academic curiosity. It touches upon our very place in the cosmos, prompting us to question the likelihood of our own existence. It's a testament to the delicate balance that allows for complexity, consciousness, and the quiet wonder of a universe capable of observing itself. The universe, in its intricate calibration, whispers a question. Why are we here to witness its breathtaking, improbable beauty? The delicate balance of cosmic laws is a profound testament to the improbable cradle that allows our existence to bloom. The anthropic principle suggests our universe is tailored for life. Consider, for a moment, the astonishing fact that the fundamental constants of our universe, The very numbers that govern everything from the strength of gravity to the mass of an electron appear to be exquisitely balanced. If even the slightest alteration were to occur in these values, the universe as we know it, a universe capable of supporting life, simply could not exist. This is the essence of the anthropic principle, a philosophical concept that, when contemplated, can offer a profound sense of perspective. It's not so much a scientific law in the traditional sense, but rather an observation, a way of framing our existence within the vast cosmic tapestry. Think of the strong nuclear force, responsible for holding atomic nuclei together. If it were just a few percent weaker, atomic nuclei heavier than hydrogen couldn't form, meaning no stars like our sun, no planets, no chemistry as we understand it. If it were a few percent stronger, stars would burn through their fuel far too quickly, collapsing into black holes before life could even begin. Or consider the cosmological constant, the mysterious energy density of empty space. If it were even slightly larger, the universe would have expanded so rapidly after the Big Bang that matter would never have had a chance to clump together, to form galaxies, stars, or planets. If it were slightly smaller, the universe might have collapsed back on itself long before it had the chance to evolve into its current state. The electric charge of the electron, the gravitational constant, the ratio of proton to electron mass, each of these, and many more, seem to be precisely tuned. It's as if the universe was designed with an observer in mind, though this is not necessarily a statement about intelligent design in a theological sense. Instead, the anthropic principle can be understood in two main ways: the weak anthropic principle and the strong anthropic principle. The weak anthropic principle suggests that our location in the universe and in cosmic history is necessarily privileged to the extent of being compatible with our existence as observers. In simpler terms, we observe the universe to be the way it is because if it were different, we wouldn't be here to observe it. It's a selection effect. Imagine a vast lottery with billions of tickets, each representing a different set of physical constants. Most of these tickets would result in a universe that is sterile and lifeless. We, as observers, find ourselves holding one of the very few tickets that allows for the emergence of life. The strong anthropic principle, on the other hand, is more speculative. It suggests that the universe must have properties that allow life to develop within it at some stage in its history. This version hints at a deeper, perhaps teleological, reason for the universe's fine-tuning. While the strong anthropic principle is more controversial and less scientifically testable, the weak anthropic principle offers a powerful, albeit humbling, perspective. It reminds us that our very existence is intertwined with the fundamental laws of nature. It's a reminder that the conditions that allow us to ponder these very questions are incredibly rare and precious. This principle doesn't explain why the constants are what they are, but it offers a framework for understanding how we can observe them to be so perfectly suited for life. It shifts the focus from a search for an ultimate cause to an appreciation of the conditions that make observation possible. It's a subtle but significant shift in perspective, encouraging us to see our place not as a random accident, but as a consequence of the universe's very nature. The sheer improbability of these constants aligning for life encourages a sense of wonder, not as a sign of divine intervention, but as a testament to the intricate and perhaps necessary relationship between the cosmos and consciousness. It's a thought that can lead to a profound appreciation for the delicate balance that allows for our very awareness, a balance that makes our brief flicker of existence possible within the grand, silent expanse. It's a reminder that the universe, in its silent, majestic way, has unfolded in a manner that, against all odds, permits us to be here, to witness, and to wonder. In the grand cosmic lottery, Our existence is a whisper of improbable perfection, a testament to the universe's gentle embrace of consciousness. The nature of time is more complex than our everyday experience. Our intuitive understanding of time, that steady, unyielding river flowing from past to future, is a remarkably useful simplification for our daily lives. We experience moments as discrete units, one following the next in an unbroken forward march. We remember the past, live in the present, and anticipate the future. This linear, absolute perception of time has served humanity for millennia, shaping our languages, our societies, and our very sense of self. However, as we delve into the profound insights of modern physics, particularly through the lens of Stephen Hawking's work, this seemingly simple concept begins to unravel, revealing a far more intricate and mind-bending reality. Time, it turns out, is not a universal constant ticking away at the same rate for everyone, everywhere. Instead, it is a dynamic, flexible dimension, intimately interwoven with space itself, forming a four-dimensional fabric known as spacetime. This fabric can be stretched, warped, and even distorted by the presence of mass and energy. Albert Einstein's theory of special relativity first introduced the revolutionary idea that time is relative. It is not an independent entity but is inextricably linked to motion. The faster an object moves through space, the slower time passes for that object relative to a stationary observer. This phenomenon, known as time dilation, has been experimentally verified. For instance, atomic clocks flown on high-speed aircraft or satellites run slightly slower than identical clocks left on the ground, precisely as predicted by relativity. This means that if you were to travel at speeds approaching the speed of light, your journey through time would be significantly slower than for those you left behind. A few years for you might translate into decades or even centuries for them. This is not science fiction. It is a fundamental consequence of the structure of our universe. But the complexity of time doesn't end there. General relativity further complicates our understanding by demonstrating that gravity also affects the passage of time. Massive objects, such as planets and stars, warp the fabric of spacetime around them. This curvature of spacetime is what we perceive as gravity, and just as motion can slow down time, so too can gravity. Time passes more slowly in stronger gravitational fields. For example, time on the surface of the Earth passes infinitesimally slower than it does in orbit, where the gravitational pull is weaker. This effect, though minuscule in our daily lives, is crucial for the accurate functioning of technologies like GPS satellites, which must constantly account for both relativistic time dilation due to their speed and gravitational time dilation due to their altitude. Hawking, in his exploration of black holes and the early universe, constantly grappled with these relativistic implications of time. He understood that in extreme environments, where gravity is immense or speeds are near light speed, our everyday notion of a uniform, universal clock breaks down completely. Furthermore, the very concept of a present moment becomes problematic when time is relative. What is simultaneous for one observer may not be simultaneous for another moving at a different speed or in a different gravitational field. This challenges our deeply ingrained sense of a shared, unfolding present. The universe, therefore, is not a stage upon which events unfold in a fixed, universal timeline. Rather, time itself is an active participant, molded by the very matter and energy that populate it. This relativistic nature of time suggests that the past, present, and future may not be as distinct or as rigidly separated as we perceive them. While we cannot, with our current understanding, travel backward in time in a way that violates causality, the interconnectedness of space and time hints at possibilities and complexities far beyond our immediate grasp. The universe is a tapestry woven with threads of space and time, and the patterns that emerge are far richer and more mysterious than our simple, linear perception allows. Even in the quiet hum of existence, time itself is a fluid whisper, bending to the grand cosmic dance. The horizon problem. Why is the universe so uniform on large scales? Imagine looking out into the vastness of the cosmos, across billions of light years. You might expect to see a chaotic, varied tapestry, a grand cosmic accident. Yet, what astronomers observe is something quite extraordinary, a remarkable uniformity. The temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang, is astonishingly consistent across the entire sky, varying by only a tiny fraction of a degree. This is the essence of the horizon problem. In our standard model of the Big Bang, regions of the early universe that are now on opposite sides of the observable sky were, at the time of the Big Bang, causally disconnected. They were too far apart to have ever exchanged light or any other information. If they couldn't communicate, how could they possibly have reached such a uniform temperature? It's like finding two people on opposite sides of a vast desert who have never met, yet are wearing the exact same, incredibly specific and unusual hat. This uniformity suggests a shared past, a common origin, a synchronized state that our current understanding of the Big Bang, without further additions, struggles to explain. The early universe in its infancy was a much smaller, more manageable place. In this nascent phase, all regions were within each other's causal horizon, meaning light could travel between them. This allowed for the exchange of energy and heat, effectively smoothing out any initial temperature variations. The problem arises when we consider how this small, uniform patch then expanded to become the immense universe we see today. If the expansion was simply a steady outward push, then the regions that are now on opposite sides of our observable universe would have been outside of each other's communication range very early on, preventing them from ever reaching thermal equilibrium. Therefore, the uniformity we observe is a profound puzzle, hinting at a period of extremely rapid expansion that occurred in the universe's earliest moments. This period, known as cosmic inflation, proposes that the universe underwent an exponential growth spurt, stretching a tiny, causally connected region to an enormous size in an infinitesimally short amount of time. During this inflationary epoch, any initial temperature fluctuations would have been stretched and diluted, while the regions that were within causal contact before inflation would have been pushed far apart, becoming what we now observe as distant, yet remarkably similar, parts of the cosmos. Inflation elegantly solves the horizon problem by providing a mechanism for the entire observable universe to have been in causal contact, and therefore able to reach thermal equilibrium before the period of rapid expansion. It's a testament to how our understanding of the universe is built upon layers of discovery, with each new observation posing questions that lead to even more profound insights about the fundamental nature of reality. The horizon problem, therefore, is not just a curiosity. It's a critical piece of evidence that points towards a more complete and sophisticated model of cosmic origins, a model that incorporates the mind-bending concept of inflation, a period of growth so immense it reshaped our understanding of the universe's very beginning. It's a reminder that the grandest scales of existence are often governed by the most subtle and elegant principles, ensuring a cosmic coherence that whispers of a unified beginning. The universe's vastness holds a silent, consistent hum, a reminder that all its distant corners once shared a single, gentle breath. The arrow of time is linked to the increase of entropy. Imagine a perfectly smooth, undisturbed pond. If you drop a pebble into it, ripples spread outwards, disturbing the calm. This process from stillness to disturbance is a one-way street. The ripples will naturally spread and dissipate. They will not spontaneously gather back together to reform the pebble and the original smooth surface. This fundamental directionality, this irreversible flow from order to disorder, is what we often perceive as the arrow of time. Scientifically, this directionality is deeply intertwined with a concept called entropy. Entropy, in its simplest terms, is a measure of disorder or randomness within a system. The second law of thermodynamics, a cornerstone of physics, states that in any closed system, the total entropy will always increase over time or, at best, remain constant. It never decreases spontaneously. This law is not about particles or forces themselves, but about probabilities. Think of it like shuffling a deck of cards. When the deck is new, it's in perfect order, low entropy. After shuffling, it becomes randomized, high entropy. It's astronomically improbable that a random shuffle will ever return the deck to its original ordered state. The universe, as a vast and complex system, is subject to this same principle. Over immense timescales, the universe tends towards a state of greater disorder. Stars burn out, galaxies drift apart, and the available energy becomes more evenly distributed, making useful work increasingly difficult. This relentless march towards greater entropy gives time its apparent direction. It's why we remember the past but not the future, why eggs break but don't unbreak, and why a cup of hot coffee cools down but doesn't spontaneously reheat itself by drawing energy from the cooler room. This increase in entropy is not a force pushing time forward, but rather a statistical inevitability that defines its direction. Without this tendency towards disorder, the concept of time as we understand it, with its distinct past, present, and future, might not even exist. The universe began in a state of incredibly low entropy, a highly ordered state after the Big Bang. From that point, it has been on an inexorable journey towards increasing disorder, and this journey is what gives our experience of time its forward momentum. It's a profound connection, suggesting that the very fabric of time is woven from the threads of increasing randomness. The universe's tendency towards chaos is, in a sense, the engine of its temporal progression, a constant unfolding from order into a more diffuse, less organized state. The universe's inevitable drift towards disorder paints the canvas upon which the river of time flows, guiding our perception from what was to what will be. The search for gravitational waves opens a new window on the cosmos. Imagine the universe not just as a visual spectacle, but as a vast, resonating chamber capable of producing its own profound music. For centuries, our understanding of the cosmos was primarily built upon the light that travels to us from distant stars and galaxies. We learned of their fiery births, their majestic lives, and their dramatic deaths, all painted across the canvas of the night sky. But what if there were other messengers, carrying even more fundamental information about the universe's most violent and energetic events? This is where the concept of gravitational waves, a cornerstone of Einstein's theory of general relativity, truly begins to shine. These are not waves of light, which are electromagnetic disturbances, but ripples in the very fabric of spacetime itself. Think of spacetime as a smooth, taut sheet. When massive objects, like stars undergoing supernova explosions, or pairs of black holes spiraling into each other, move and accelerate, they create disturbances in this sheet, like dropping a pebble into a still pond. These disturbances propagate outwards at the speed of light, carrying with them information about the source that created them, its mass, its spin, its motion. For decades, gravitational waves were purely theoretical, a prediction of Einstein's genius that remained elusive. Detecting them presented an almost insurmountable challenge. The distortions they cause in spacetime are incredibly tiny, far smaller than the width of an atom. To put this into perspective, if you were to stretch a ruler the size of the Earth, A passing gravitational wave would alter its length by less than the diameter of a single human hair. This minuscule distortion required extraordinarily sensitive instruments and the development of interferometers like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo was a monumental feat of engineering and scientific ingenuity. These detectors use lasers split into two beams that travel down long, perpendicular arms. If a gravitational wave passes, it slightly stretches one arm while compressing the other, causing a minute change in the distance the laser beams travel. By precisely measuring the interference patterns of these beams when they recombine, scientists can detect these infinitesimally small changes. The first direct detection of gravitational waves in 2015, originating from the merger of two black holes, was a watershed moment in astrophysics. It was the first time we had heard the universe in a way that was fundamentally different from seeing it. This opened up an entirely new avenue for observing cosmic phenomena, allowing us to study events that are invisible to traditional telescopes, such as the collision of black holes or neutron stars. These events, occurring billions of light years away, are some of the most energetic in the universe, and gravitational waves provide a direct, unhindered glimpse into their chaotic dance. Moreover, the study of gravitational waves allows us to probe the extreme physics of gravity in ways that are impossible to replicate on Earth. They offer a way to test Einstein's theory in its most rigorous regimes and potentially reveal new physics that lies beyond our current understanding. It's as if we've been listening to the universe with only one ear, and now, with gravitational waves, we can finally hear its full symphony. Through the subtle tremors of space-time, the universe whispers its most profound secrets, revealing the silent, violent ballet of cosmic giants. String theory offers a potential framework for quantum gravity. Imagine, if you will, the very fabric of reality. We've spoken of the grand, sweeping curves of space-time, governed by Einstein's magnificent theory of general relativity, describing the universe on the largest scales, the orbits of planets, the collision of galaxies, the very expansion of the cosmos. And we've touched upon the bewildering, probabilistic dance of quantum mechanics, the realm of the infinitesimally small, where particles can be in multiple places at once and where uncertainty reigns supreme. These two pillars of modern physics, general relativity and quantum mechanics, are incredibly successful in their respective domains. Yet, they stand in stark contrast, a fundamental disconnect that physicists have long sought to bridge. When we try to apply the rules of quantum mechanics to the immense gravitational forces predicted by general relativity, particularly in extreme environments like the heart of a black hole or the very instant of the Big Bang, our equations break down. They yield nonsensical, infinite results, signaling that our current understanding is incomplete. This is where the elegant, albeit complex, world of string theory enters the conversation, offering a potential pathway to a unified description of all fundamental forces, including gravity. At its core, string theory proposes a radical departure from our conventional view of fundamental particles. Instead of point-like entities, the ultimate constituents of the universe, according to string theory, are not zero-dimensional points but one-dimensional vibrating strings. These strings are unimaginably small, far beyond our current ability to observe directly, on the order of the Planck length, which is about 10 meters. Think of a violin string. Depending on how it vibrates, it can produce different musical notes. In string theory, these fundamental strings, also unimaginably small, vibrate at different frequencies and in different patterns. Each distinct pattern of vibration corresponds to a different type of fundamental particle. So an electron, a photon, a quark, all the building blocks of matter and energy as we know them, are simply different notes played by these fundamental strings. This is a profound shift in perspective. It means that the seemingly diverse array of particles we observe are not fundamentally distinct entities, but rather manifestations of a single underlying entity, the vibrating string. But the implications go much further. In many versions of string theory, these strings can be open, with distinct endpoints or closed, forming loops. The vibrations of these strings can give rise to all the known fundamental forces, including electromagnetism, the strong nuclear force, the weak nuclear force, and crucially, gravity. In this framework, the graviton, the hypothetical quantum particle that mediates the force of gravity, emerges naturally as one of the vibration modes of a closed string. This is a monumental achievement, as it offers a way to incorporate gravity into the quantum framework without the mathematical inconsistencies that plague other approaches. Furthermore, string theory often requires the existence of extra spatial dimensions beyond the three we perceive: length, width, and height, plus time. These extra dimensions are thought to be curled up or compactified to an incredibly small scale, making them invisible to us in our everyday experience, much like how a garden hose appears one-dimensional from a distance, but is actually two-dimensional up close. The number of these extra dimensions can vary depending on the specific formulation of string theory, with 10 or 11 spacetime dimensions being common. These extra dimensions are not just an abstract mathematical curiosity. They play a crucial role in determining the precise ways strings can vibrate, and consequently, the properties of the particles and forces they create. The mathematics of string theory is incredibly rich and intricate, leading to profound insights into the nature of spacetime and the fundamental laws of physics. It has provided new perspectives on black holes, suggesting that they might be understood in terms of strings and brains, higher dimensional objects, and has offered potential solutions to the long-standing black hole information paradox. While string theory is still a theoretical framework, and direct experimental verification remains a significant challenge due to the extreme energies and scales involved, it represents one of the most promising avenues for a complete and consistent description of the universe, a true theory of everything that can reconcile the seemingly disparate worlds of the very large and the very small. It is an ongoing journey of discovery, pushing the boundaries of our understanding of reality. In the quiet hum of existence, the universe's fundamental melody is played on strings, revealing that even gravity's embrace is woven into the dance of cosmic vibrations. The limits of our knowledge are as fascinating as what we know. There's a profound truth that often whispers at the edge of our understanding, a truth that Stephen Hawking, in his tireless pursuit of cosmic secrets, often found himself contemplating: that the boundaries of what we don't know can be just as awe-inspiring, just as intellectually stimulating, as the vast expanses of what we do understand. For so long, humanity has striven to map the universe, to quantify its forces, to predict its future. We've built telescopes that peer into the deepest reaches of space and time, developed equations that describe the ballet of celestial bodies, and devised experiments that probe the very fabric of reality. Yet, with every answer we uncover, a new galaxy of questions unfurls. Consider the nature of dark matter and dark energy, which together constitute roughly 95% of the universe's mass energy. We can observe their gravitational effects, their influence on the cosmic expansion, but their fundamental composition remains an enigma. We have names for these phenomena, powerful descriptive labels, but the underlying particles, the true mechanisms at play, are still shrouded in mystery. This isn't a failure, it's an invitation. It's an indication that the universe is far more complex, far more intricate than our current models can fully encompass. Hawking's work on black holes, for instance, pushed the boundaries of general relativity and quantum mechanics, revealing the tantalizing possibility of a singularity at the heart of a black hole, a point where our current laws of physics break down entirely. This breakdown isn't a dead end, but a signpost pointing towards the need for a deeper, more unified theory of everything. Similarly, the question of what existed before the Big Bang, or what lies beyond the observable universe, pushes the limits of our current cosmological frameworks. These are not trivial inquiries. They are the grandest philosophical and scientific challenges of our era. The very act of acknowledging these limits, of embracing the unknown, is what drives scientific progress. It fuels our curiosity, ignites our imagination, and compels us to develop new tools, new theories, and new ways of thinking. The universe, in its vastness and complexity, is not merely a collection of facts to be catalogued, but a grand, unfolding mystery. And it is in grappling with the edges of that mystery, with the profound questions that lie just beyond our current grasp, that we truly begin to appreciate the scale and wonder of existence. The limitations of our knowledge are not a source of frustration, but a testament to the infinite, unfolding beauty of the cosmos, a constant reminder that there is always more to explore, more to discover, and more to marvel at. In the quiet expanse of the unknown, our greatest discoveries often lie waiting, reminding us that the journey of understanding is as infinite as the stars themselves. The universe's ultimate fate remains an open, profound question. The grand tapestry of existence, woven from the threads of stardust and governed by the elegant laws of physics, holds within it a profound mystery. What will become of it all? For millennia, humanity has gazed at the stars, pondering not just where we came from, but where we are going. Stephen Hawking, with his unparalleled intellect and relentless curiosity, pushed the boundaries of our understanding. But even his work points towards the vastness of the unknown when it comes to the cosmos's final act. The ultimate fate of the universe is not a single, predetermined outcome, but rather a spectrum of possibilities, each more awe-inspiring and humbling than the last. These possibilities are largely dictated by the interplay of fundamental forces and the enigmatic components that make up our universe. One of the most significant factors influencing this grand finale is the nature of dark energy. We've observed that the expansion of the universe is not only ongoing, but is actually accelerating. This acceleration is attributed to dark energy, a mysterious force that seems to permeate all of space and exert a repulsive gravitational effect. If dark energy remains constant, as described by the cosmological constant, the universe is destined for a big freeze or heat death. In this scenario, galaxies will continue to drift apart, stars will eventually exhaust their fuel, and the universe will become an ever-expanding, increasingly cold and dark expanse, approaching absolute zero. All activity will cease, and the universe will be a silent, empty void. However, the nature of dark energy is not fully understood. If dark energy were to strengthen over time, a more dramatic and abrupt end could occur, a scenario known as the Big Rip. In this chilling possibility, the accelerating expansion would eventually become so powerful that it would overcome all fundamental forces holding matter together. First, galaxies would be torn apart, then stars and planets, and ultimately, even atoms themselves would be ripped asunder. This would be a swift and violent end, dissolving all structure into a state of ultimate dispersal. Another, albeit less favored by current observations, possibility is a reversal of cosmic expansion, leading to a big crunch. If the density of matter and energy in the universe were high enough, or if dark energy were to somehow change its nature and become attractive, gravity could eventually halt the expansion and cause the universe to contract. This contraction would accelerate, with galaxies rushing towards each other, temperatures soaring, and all matter collapsing back into an infinitely dense singularity, perhaps mirroring the conditions of the Big Bang itself. This cyclical view of the universe, where a big crunch could potentially lead to another Big Bang, offers a tantalizing, albeit speculative, vision of cosmic rebirth. The ongoing research into dark matter and dark energy, the very constituents that appear to dominate the universe, are crucial to refining these predictions. Experiments searching for the subtle effects of dark energy and mapping the large-scale structure of the cosmos are constantly providing new data that helps us inch closer to understanding these cosmic enigmas. The very act of questioning the universe's end is a testament to our innate drive to comprehend our place within it. It is a philosophical and scientific pursuit that connects us to the grandest of scales, reminding us of the ephemeral nature of our own existence against the backdrop of cosmic time. The fact that we can even contemplate such vast futures, and that our current understanding, though incomplete, allows for such profound speculation, is a marvel in itself. The universe, in its ultimate uncertainty, offers not despair, but an invitation to wonder and to appreciate the present moment, the fleeting era of cosmic activity that we are privileged to inhabit. The universe's grand narrative is still being written, its final chapter a question mark that invites us to marvel at the present, knowing that even in its unknowable end, there is a profound beauty in its unfolding. Our existence is a fleeting moment in cosmic history. Consider the vastness of cosmic time, a tapestry woven with billions of years. Our planet Earth has existed for approximately 4.5 billion years. This sounds like an immense duration, and indeed, it is long enough for the complex dance of evolution to unfold, for life to emerge, diversify, and eventually give rise to conscious beings like ourselves. Yet, when we place this 4.5 billion years into the grander narrative of the universe, it becomes a mere blink. The universe itself is estimated to be around 13.8 billion years old, originating from the Big Bang. If we imagine the entire history of the universe as a single, 24-hour day, the Earth would have formed only in the late afternoon, and the entire span of human civilization, from our earliest ancestors to the present day, would occupy the final few seconds before midnight. This perspective is not meant to diminish the significance of our lives or the preciousness of our experiences, but rather to offer a profound sense of scale. Our individual lifespans, typically measured in decades, are even more infinitesimally small within this cosmic timeline. The birth and death of stars, the formation and collision of galaxies, the ebb and flow of cosmic structures, these processes unfold over timescales that dwarf human comprehension. Even the existence of our species, Homo sapiens, is a relatively recent phenomenon, appearing only in the last few 100,000 years, a mere whisper in the cosmic wind. The geological epochs, the rise and fall of dinosaurs, the very formation of continents, all these immense transformations occurred long before we were here to witness them, and will continue long after our time has passed. This realization can be both humbling and liberating. It places our struggles, our triumphs, and our anxieties into a broader context, highlighting the ephemeral nature of all things, including ourselves. It encourages us to appreciate the present moment, to recognize the extraordinary rarity of conscious existence within the silent, indifferent expanse of the cosmos. The universe, in its immense age and scale, continues its majestic unfolding, oblivious to our fleeting presence. Yet we, as products of this grand cosmic evolution, are capable of contemplating its immensity, a testament to the remarkable journey that has brought us to this point. The very act of observing and understanding the universe is a remarkable achievement, a brief spark of awareness in the vast, dark ocean of existence. Each moment we are alive is a unique confluence of cosmic events that will never be replicated. Therefore, to truly grasp our place in the universe is to understand that our existence, though brief, is a precious and improbable gift, a fleeting but beautiful phenomenon within an eternal, ever-changing cosmic drama. The sheer improbability of our consciousness arising, of our ability to ponder these very questions, is a source of deep wonder. We are, in a sense, the universe experiencing itself, a momentary, self-aware eddy in the vast river of space-time. This ephemeral nature underscores the importance of cherishing our time, of living with awareness, and of seeking understanding in the face of cosmic immensity. The stars have been burning for billions of years, and will continue to burn for billions more, their light traveling across unimaginable distances to reach us, a reminder of the ancient past and the distant future. Our brief candle of existence is lit against this backdrop of eternal cosmic processes, a poignant reminder of our transient yet meaningful place. And in this brief, luminous flicker, we find the quiet awe of being. The wonder of the cosmos invites us to dream beyond our grasp. Our journey tonight, through the profound discoveries and elegant theories that illuminate the universe, has led us to a point of quiet contemplation. We have traversed the vastness of space-time, marveled at the enigmatic nature of black holes, and felt the subtle, yet powerful, influence of gravity. We have touched upon the foundational principles of quantum mechanics and the grand architecture of general relativity, and glimpsed the immense mysteries that still lie beyond our current understanding, such as dark matter and dark energy. We have considered the very origins of our universe, the echoes of the Big Bang resonating through the cosmic microwave background, and the ongoing expansion that stretches the fabric of reality itself. The scientific endeavor, particularly as illuminated by minds like Stephen Hawking, is not merely about accumulating facts. It is about fostering a profound sense of awe, a deep appreciation for the intricate ballet of cosmic forces, and a humbling recognition of our place within this grand, unfolding narrative. It is this very wonder, this inherent curiosity that the universe sparks within us, that compels us to look beyond the immediate, the familiar, and even the presently conceivable. It encourages us to imagine possibilities that stretch the limits of our imagination, to ponder questions that may not have immediate answers, and to embrace the unknown not as a void, but as a fertile ground for future discovery. This sense of wonder is a gentle, persistent invitation. It whispers to us in the silent expanse between stars, in the elegant curves of spacetime, and in the fundamental laws that govern existence. It is an invitation to expand our perspective, to see our own lives not as isolated events, but as integral threads woven into the magnificent tapestry of the cosmos. It encourages us to dream of what lies beyond the observable horizon, to consider the vastness of what we do not yet know, and to find a profound peace in that very realization. The universe, in its infinite complexity and staggering beauty, offers us a profound opportunity to transcend our limitations, to connect with something far greater than ourselves, and to find solace in the sheer, unadulterated marvel of it all. This is the ultimate gift of scientific exploration, the awakening of a deep, abiding wonder that lifts us, ever so gently, towards the infinite possibilities of existence, encouraging us to dream, to explore, and to find a profound sense of calm in the face of such magnificent mystery. The boundless cosmos, in its silent majesty, whispers to our souls, urging us to dream beyond the edges of our known world, and in doing so, to find a quiet peace within its infinite embrace. Our calm exploration has covered the profound discoveries and theoretical landscapes illuminated by Stephen Hawking, charting a course through the very fabric of space-time, the enigmatic nature of black holes, and the grand expansion of our universe. We have journeyed from the edge of time to the fundamental principles that govern existence, touching upon the mysteries of dark matter and dark energy, the echoes of the Big Bang, and the persistent quest for a unified theory. We've considered the surprising insights into black hole evaporation through Hawking radiation, the mind-bending implications of the information paradox, and the philosophical ponderings of the multiverse and fine-tuning. Tonight, we have reviewed the principles of gravity's dominion, the delicate dance of quantum mechanics and general relativity, and the vast, accelerating cosmos that surrounds us. Each concept, from the warping of space-time to the potential evaporation of black holes, serves not just as a scientific fact, but as a gentle reminder of the immense, intricate, and often counterintuitive nature of reality. It is a reality that stretches far beyond our immediate perception, a tapestry woven with forces and phenomena that inspire a quiet awe, a profound sense of perspective. Consider how these grand cosmic narratives, these explorations of the infinitely large and the unimaginably dense, can help us to feel a little smaller, a little less burdened by the immediate anxieties that can grip our minds. The universe, in its vastness and its intricate laws, operates on scales and with principles that dwarf our daily concerns. To contemplate the slow, majestic unfolding of cosmic history, the enduring power of gravity, or the theoretical limits of our understanding, is to gain a sense of our place within something far greater, far more enduring. This perspective can be a soothing balm, a gentle release from the urgency of our waking thoughts, allowing the mind to soften and to yield to the quiet embrace of rest. The universe does not hurry, yet all is accomplished. Like the slow, deliberate unfolding of a nebula or the patient, immense journey of light across galaxies, our own journey towards sleep can be one of gentle surrender. The complex equations, the mind-bending theories, the very edge of time and space, these are not meant to stress, but to inspire a quiet wonder, a philosophical curiosity that can lull the restless mind. They are invitations to ponder, to marvel, and ultimately to let go. So, as we conclude this gentle exploration, allow the immensity of the cosmos to wash over you, not as a burden, but as a comforting blanket of perspective. The stars have been burning for billions of years, and they will continue to shine long after we have rested. The laws of physics are constant, reliable, and profoundly beautiful in their complexity. You are a part of this grand, unfolding story, a fleeting but precious spark in the vastness. It is time to rest now. Allow the quiet wonder of the universe to guide you into a deep, peaceful sleep. Let the vastness cradle your thoughts and the fundamental principles of existence bring you a profound sense of calm. Sleep well. Good night. It is time to rest now. If you happen to still be awake, you can drift into the next chapter now, continuing our journey through the quiet wonders of the cosmos.